All right, so this is what we are to prove. So this incident to mirror one incident reflected. Then this is also a reflection to mirror two. Okay. First, and since this is parallel to this, if this is theta, obviously this will also be theta. And also, Eresi, we are here. And mute yourself, okay? Okay, so once this is a normal incident reflected, so normal, we have angle of incidence. We also have angle of reflection, which is equal to the angle of incidence. Then this would also be theta. Let me assume to increase this a little bit. So this is the emergent ray. Once this is incident and reflected, when I draw a normal N2, this is maybe Y, this will also be Y. So that this is 90 minus Y. Once this angle is beta, this is also beta. So when we look at this, to mirror one, we have 2 times I plus 2 times theta equal to 180 degree as equation 1. If we look at this triangle, we also have 2 theta plus 90 minus y, giving us 180 degrees. Then finally, to this right angle triangle. Okay, I think to help understanding, let's label it A, B, C, D. Yes. So this equation refers to triangle A, B, C. This equation refers to sum of angles at C. Summation of angles at C. Then, when we look at triangle, oh, okay, CBD, we can also say that 2I plus 2Y plus beta equals 180 degrees. Okay, so when we make y the subject here and substitute into this relation, we can eliminate y. All that we are doing is I want to eliminate the variables. Please, if you haven't muted, mute, okay? So in equation, from equation 2, let's make y the subject. Y will be equal to 2 theta plus 90 minus 180. That is, we are only moving y to this end, and that will be positive. So y will just be this. Let me check on who. Nanama, please mute yourself for us. Okay, so having made y the subject from equation 2, okay, let's substitute it into equation 3. So 2i plus 2 times, this is y is equal to 2 theta minus 90 plus beta is equal to 180 degree. Okay, so let's simplify what we have there. We have 2i plus 4 theta minus 2 times 90. Okay, this is 180 plus beta again equals 180 degree. All right. We are just substituting. So 2i plus 4 theta plus beta equals 360. Negative 180 crossing the equal sign. So plus 360. So now we have equation 1 and what we will call as equation 4. So let me rewrite the equations that are left now. We have 2i plus 2 theta is equal to 180. Then 2i equation 4 plus 4 theta plus beta equals 360. Okay. If we make 2i the subject from equation 1 and substitute into equation 4, let's make Amma.
Sir, please could you show us the downside? I want to ask something there, but like
Okay.
sir, please the y when you
Mhm.
substituted, y is 90 negative.
I'm substituting from equation 2. Let me see. Oh, I'm making y the subject from equation 2. So that will be 2i. I'm coming on. I'm coming. Okay, from equation 2, y will be equal to 2 theta plus 90 minus 180. So when you subtract 180 from 90, it is equal to negative 90. Have I answered you?
Yes.
So it's from here, 90 minus 180. All right.
Okay. Yes, please.
All right. I think I was jumping. So let me to help some of you, let me I think take my time to do it. So after making this the subject, y the subject in equation 2, I then substituted it into equation 3. Okay. So
Please.
let me take my time to help. But Reza, I'm recording. Oh, okay. Maybe you also want to. So hello, hold on. Let me take my time to explain this thing to you. So after making y the subject in equation 1, so from equation 2, make y the subject. Okay, and that would give you this. Okay, after making y the subject, substitute this. Substitute this in equation 3. And this equation 3. So wherever I see y, I substitute this. So I have 2i plus 2 times 2 theta plus 90 minus 180 bracket close plus beta is equal to 180 degrees. Then I expand. When you expand, you have 2i plus 4 theta plus 180. Okay, I must even subtract. So 90 minus 180 is minus 90. So this will give us minus 180 after subtracting the multiplying by 2. Please, are we okay here? Are we okay
Yes,
here?
yes.
Okay, so plus beta is equal to 180. So that we are regrouping like terms. We have 2i plus 4 theta is equal to plus beta is equal to 180 plus 180, which is 360. And this is what I'm calling as equation 4. Okay, so you now have equation 4 and equation 1 to deal with, and that is what is written here. Okay, since we have 2i and 2i, make 2i the subject in equation 1 and substitute into 2i in equation 1 is 180 minus 2 theta. So we have, then substitute this into equation 4. So you have 180 minus 2 theta plus 4 theta plus beta is equal to 360. Okay. Group like and 4 theta minus 2 theta. So you have 2 theta, okay, plus beta is equal to 360 minus 180. You have 180 degree. We are proving this. So when you make beta the subject, then you can be smiling to the bank. When you are doing this, and after getting to the last stage, you are seeing the resemblance of what you have to work, then you begin to smile. When you are not getting it, then you'll be weeping within. Okay, so this is the proof. So how did we get it? You get it by using the same rule. Once this ray is the incident ray to M2, once it's parallel to this, when two lines are parallel, they have the same gradient. So theta, this will also be theta. When you draw a normal, the angle between the incident ray and the normal I, the angle between the normal and the reflected ray also R, but they are equal by the law of one of the laws of reflection. So I, this will also be theta. You apply the same thing at the point B. At the point B, normal y 90 minus y. Then you sum up total angles at C. Then sum up the angles at triangle ABC. When you finish, you consider triangle BCD. Then get the equations. Yeah, some of you actually got it right. Some of you got it right, but I wasn't pleased with your answers. It is just, it doesn't follow that orderly thing. That's the problem I saw with some of the solutions I had. Any question? Amma,
No, please.
Amma, what's your question?
Mr. Yeah, please, if can you also see the line BC as the emerging ray? No, I mean line BD as the emerging ray and line BC as the incident ray.
Oh yes, that's the
Please.
BD. This is the ray we are calling as the emerging ray. Okay, and it's BD is part of the emerging ray. Okay,
Sir,
and
please.
then DC as the incident.
Sir, please.
Mhm.
How I did mine, no. The answer now I got it from the triangle ABC.
Mhm. ABC.
Yes.
Now I think yes, you got it, but I have to look at what you presented or submitted to make meaning of how you did it. Okay.
Okay, sir.
All right. Then there is this other question.
Mr. Dia,
Hello, Grisla.
Mr. Dia, why didn't you make that glancing angle theta, but you made it 90 minus y?
Because you see this line, the emerging ray. Grisla, emerging ray.
Yeah.
Does it look like parallel to this mirror? Grisla.
No, please. No, please.
Yes, that's the reason why. It doesn't, this one, the incident ray looks like parallel to this mirror. But the emerging ray doesn't look like parallel to this. That's the reason. Okay.
Okay.
Am I again?
Yes, sir. Sir, please, what she's talking about, that's what I did.
So if you see, perhaps you considered it and then got it right, but the point is that this ray from the diagram I sent to you doesn't look like parallel to this one. The reason for me looking at it looking at it differently, right?
Yes.
Then the monkey question. In fact, only a few of you attempted the monkey question, the first problem of the day. You see, it's a very simple question, but maybe you couldn't make enough time to think through. And one thing about me is that in my exams, I try to, these are the sort of questions usually I'm interested in. Questions which would force students to at least think small. It's not difficult, but on the face value, you may think it's so. And the question is about Newton's laws, especially second law, that whenever there is a net force or resultant force, a body would accelerate. Whenever there is a net force, body would accelerate. If there's no net force, what happens? Priscilla, if the net force is 0, what happens?
Mr. Dia, the body moves at constant velocity or at rest.
Exactly. I don't know. So this is what you need. These two stuff, okay, are what you need to solve the problem. A monkey of mass 40 climbs on a rope which can withstand a maximum tension of 600 Newton. So this is the fixed point representing the tree. We are not here to draw. So this is the rope. Can I even draw a monkey? Whatever. Okay. So these are the legs of the monkey. Of course, a monkey has a tail. At least this monkey is beautiful. So the mass of the monkey is 40. Then we are told that there's tension within the string. The tension is always directed to the points of support. So it will be, the tension will be here. The maximum tension in the string, we are told T maximum is equal to 600. And the tension is there, is that strength, force within. Now, what you must understand is that if the maximum tension is this, then it means any force or weight subjected to the rope, which goes beyond the tension. Please let me pick this call and then get back to you, okay? It's an urgent call from school. So the maximum tension means that the maximum strength, okay, within the string or the rope. This is similar to, you see, when a rope is tied to something and whoever is hanging on the rope has a weight greater than the tension within the string, what happens? What happens to the string? It breaks.
Yes.
So that is exactly what we are going to look at. So when the body accelerates, okay, in any direction, what happens to the tension? So in I, we are told that if the monkey climbs up with an acceleration of 6 meters per second squared. So if the monkey climbs up, with an acceleration equal to 6 meters per second, what happens? Okay, now let's look at the total force acting on the monkey. We have the tension in the string pointing up to the line of support, and we have the weight of the monkey, mg. So if the monkey is climbing up with this acceleration, then class, what will be the net force acting on the monkey? What will be the net force here? Yes, if the monkey is climbing up, the tension in the string acting here, and then the monkey's weight acting downwards, what then will be the net force acting on the monkey? Somebody to help me. What will be the net force here? Hey, anybody? All right.
Yeah, 204.
Pardon?
240.
240, I don't get it. Okay, so we have the tension in the string acting up, and then the weight of the monkey acting down. These are the forces on the monkey. So the net force must be because the monkey is climbing up, the tension in the string must be greater than its weight to climb. If it is the other way around, if the weight is greater than the tension, the rope breaks. It cannot climb. So once the monkey is climbing up with this acceleration, then it means that the tension must be greater than its weight. That's the only condition where it can climb up. So the net force will be the tension in the string minus the weight. Now Newton is saying that every net force or resultant force, whenever there is a resultant force, then a body accelerates. So the resultant force is equal to the mass of the body times the acceleration. This is Newton's second law. So we equate the net force to MA. So MA would be equal to T minus mg. Are we okay here?
Yes.
So if the net force or the resultant force is Ma, and we are equating it to our resultant force in this case, then if we make tension in the string the subject, we have Ma plus mg, which is M out, A plus G in. M is the mass of the monkey, which is 40 times acceleration. The monkey is accelerating up 6 plus acceleration due to gravity 10. So we have 40 times 16. And what is 40 times 16?
640.
This is 640 Newton. What it means is that for the monkey to accelerate up to this value of acceleration, the tension within the string to support the monkey must be 640. For the monkey to accelerate up, okay, to the magnitude of this acceleration, the tension that must be within the string to support the monkey must be 640. So if we are giving the maximum tension to be 600, would the brake, would the rope break or be intact?
Break.
It will certainly break. So because 640 is greater than the maximum tension, which is 600, rope would therefore break, or the brake would rope. Okay, let's look at the other situation. Let's look at the other situation. B, if the monkey climbs down with an acceleration of 4 meters per second, Eresi.
Mr. Dia, he said when the rope will break because the tension is less than the 640. But sir, it's just a few, this one underneath the 640. So like can't the monkey like hurry up and jump or something?
The monkey has no idea of the tension in the rope. It is the same as Eresi. I have a rope tied to a tree. Okay, try if you can climb up. You have no idea of the tension in the rope. But when it happens that your weight is greater than the tension in the rope, naturally it will break. So the monkey has no idea of the tension. You are using your physics to calculate something that in case this is the situation, what will happen? Erase, are you okay?
Yes, sir, but sir, will the rope break before the monkey climbs it, or it will break after it has climbed to a certain point?
When the monkey attempts to accelerate by that magnitude, it will break, because by doing that, the tension that must support, okay, the acceleration must be 640, and what is there is not up to it. Okay.
Okay, thank you.
I saw another hand. Please, if your hand is up, go ahead.
Mr. Dear,
Hello, Charlotte.
please, you see, we noticed that tensional force is directly proportional to acceleration.
Come
So,
again.
does it mean that tensional force is directly proportional to acceleration?
Who
So,
said
does it
it?
mean that
Charlotte, who said it?
T's got M is so? It means if tensional force increases, acceleration will increase per the formula we have here. Or
Neighbor, I'm taking a shot of. I'm coming. Let me drop attendance into the group, okay? Else, your parents may think a lot of you didn't show up. I'm coming. Charlotte, I'm coming, eh?
yes, please.
He said from the
Equation.
yes.
Tensional force is directly proportional to acceleration, right? Or
Yes.
So I'm saying that if
I partially,
partial.
directly proportional to the mass and acceleration. So here the mass is constant. So as for G is constant.
Yes, please. So please, if the monkey is to move at as an acceleration lower than 6, does it mean that it might not the rope might not break?
It was a good question because we have a value like that. So let's look at it and make the judgment yourself, okay?
Yes, please.
So the next question is that B climbs down with an acceleration of, okay, Charlotte, here it is climbing down, but let's assume if this value A is 4, certainly it will reduce the tension, because if this is 4, we have 4 plus 10, which is 14 times 40. And what will be 14 times 40? Charlotte?
560.
560. Still greater than the tension, but we could see that when the acceleration is reducing, tension would also reduce. To answer what you said, is that okay?
Yes, please.
But I want you to look at what happens if the monkey climbs down with an acceleration of 4 meters per second squared. If the monkey climbs down with an acceleration of 4 meters per second squared, what will happen? I think because of time, let me quickly do it. So we are looking at this time, the monkey climbing down with an acceleration of 4 meters per second squared. Okay, so what will be the net force? Every acceleration must be caused by a net force. Okay, but this time the monkey is also climbing down. Okay, climbing down with an acceleration equal to 4. So what will be the net force acting on the monkey? What will be the net force acting on the monkey this time? Yes, Yaba?
Please, the weight of the monkey minus the tension.
Exactly. Once the direction of the monkey has changed, then the tension must be enough to support its weight. So this time around, the net force will be the weight mg minus the tension, because the direction has changed, okay? And so the tension must be enough to. So the direction this time, I don't want to draw another monkey, but the monkey's direction has changed. It is climbing down. So mg minus t will give us the net force. So the acceleration, okay, ma must be equal to mg minus t. Therefore, t would be equal to mg minus ma, which then will be equal to m out g minus a. 40 by 10 minus 4. So we have 40 by 6. And this is 240 Newton. So for the monkey to climb down by that magnitude of acceleration, then the tension to support this acceleration downwards must be 240. Compare this to the maximum tension in the string. So would the rope break or be intact?
It will be intact.
Exactly. It will be intact. Nothing will happen to it. The monkey can successfully climb down. Then the last, is it the last or the third one? Is that C? C climbs up with uniform speed of 5 meters per second. Within 3 minutes, I want you to think through and answer it for me. What happens if the monkey climbs up with uniform speed of 5 meters per second?
Mr.
Within 3
Edgar,
minutes. Hello.
please, about this one. You said because it is moving down,
Yes.
the force is equal to weight minus t. So are you trying to say the weight will be greater than the tension?
The weight must be greater than, okay, that the tension in the opposite to enable it climb down. So mg, okay, minus tension would give us the net force.
Okay.
Mr. Edia.
Mm-hmm. Hello.
Mr. Edia, please. So, like, does it mean because the monkey is already on the rope, it means like the tension was already able to support the monkey? Like, I don't know whether you get my question.
No. Come again.
Like, you see, like the monkey is already on the rope, so it means the rope is already able to support the monkey.
What I'm saying is that if the monkey is climbing down with an acceleration of 4, okay, then here its weight must be greater than the tension to give us that acceleration of 4. So if you are looking for the net force which must produce that acceleration, it is when we subtract the tension from its weight. So mg minus t would give us the net force. Are you okay?
Okay.
Now,
Yes, please.
our consideration is that we don't know what the tension is.
Mr. Adrian.
Okay, so we find the tension and compare it with the maximum tension which we've been told. If the tension is less, then it means it's less than what we've been given as 600. Then the monkey can accelerate down. If it is greater, then the rope breaks, as we saw in the first situation.
Mr. Adrian.
Hey, Inshira. Inshira, go ahead.
Please, has the position of the monkey changed the equation?
Yes.
I'm saying
Yeah.
how does
Mhm.
I'm saying how does it change the whole
Okay.
equation?
So if this is it, the tension is always directed to the support. Okay. If an object is accelerating upward, its weight is always in line with gravity, mg. So if you have forces acting on a body, one of the force acting upward, another acting downward, okay? If the body's motion is going up the rope, then T must be greater than mg for the body to go up the rope. Because if mg is greater than T, the rope breaks. It is similar to Inshira. I've suspended a rope. Climb. Just climb on it. Inshira, if your weight is greater than the tension, it will tear off. Right?
Yes,
Inshira.
sir.
So for
Yeah.
you to climb up, then the tension must be enough to support your weight. So if you are going up, then the net force which is causing your acceleration would be equal to T, this T minus mg, because T must be greater than mg for you to be able to move up, accelerate. If the body is accelerating downwards, okay, monkey is accelerating downwards, then for the body to accelerate downwards, then this time around, the weight, because we are the whole motion is in the direction of the weight. The weight must be greater than the tension to give us that acceleration. Israel, are you okay?
Yes, yes.
Now,
Thank you.
welcome. The third question, please, have you tried it, and what did you get for that? Monkey climbs up with uniform speed of 5 meters per second. Monkey climbs up with uniform speed of 5 meters per second.
The rope will not break
Why? Why? Charlotte?
because
Because you won't break it.
because the tensional force is equal to the mass times gravity.
Why, Charlotte? Why?
Because acceleration is equal to 0.
Fantastic. But why?
Hey, mistake.
But why?
Because he said it's a constant velocity, so means there is no
Exactly.
changing.
Yeah. Why? Chrysler, that is what you answered earlier. If a body moves with a constant velocity, acceleration is 0, meaning that the net force acting on the body is 0. Dynamic equilibrium. If a body is stationary, you continue to be stationary. Okay. If it's also moving, it will continue to move in a straight line with a constant velocity unless an external force acts on it. So for static equilibrium, the net force is 0. For dynamic equilibrium, the net force is 0. So if the monkey is moving up with that constant velocity, it means that then the tension within the string or rope, okay, is equal to the weight of the monkey. So T minus mg is equal to 0. The net force is 0. Or T is simply equal to mg if body moves at a constant velocity. Okay, so if T is equal to mg, then this will simply be 440 times 10, giving us 400 Newton. So that when we compare with the maximum tension within the rope, we realize that this is less, and so rope will not break. And so rope will not break. Let me resend the question so that at least those of you who do not have it will still have it and copy. Then we look at the last question. The last question is that what happens if the monkey falls down the rope nearly freely under gravity? Even with this particular situation, if we don't even calculate, we can determine what will happen. Priscilla, what will happen if the monkey falls freely from the rope? Nearly, yes, under gravity. What will happen?
Mr. It
won't break. If the monkey decides to just fall, okay, get off from the rope and fall under the influence of gravity, free falling, the rope will not break. How do we use mathematics to show this? The monkey is falling, so the direction is downwards. Okay. If the direction is downwards, then mg minus the tension must be equal to, when the monkey is falling, what is the net force acting? What is the net force acting on the body, on the monkey? If the monkey is falling, what will be the force acting on the body during the course of falling? Gravity. Gravity, force of gravity. And how do we calculate for the force of gravity on the body? How do we calculate? M, the mass of the body, times the constant acceleration due to gravity. Okay, so what happens is that we have T is equal to mg minus mg. So the tension in this case is equal to 0. So if the tension to do this is equal to 0, then we compare it with the maximum tension. Would the rope break or be intact?
It will be intact.
Exactly. Okay. So if you have any question, ask. If you don't have any question, let's move on to formation of images in plane mirrors as we were looking at last time. Please, those of you who are joining us for the first time, we've started optics lights, but we are currently on formation of images in plane mirrors. Okay, plane mirrors, very, very plain. Spherical mirrors is a bit deep or loaded. Can I clean the board? Can I?
Yes, please.
This monkey question, I'll give it to your teachers. When you come, it will be put in a different way for one of the exams. So spend time to go through it. Change values and try your hands on the question because I'll give it out to them to test you. Hello. Hello.
Mr. J, please, it's nothing.
Yo, better. Okay, well, where's my ruler? Coming. I don't know where I dropped this. Good. So formation of images in a plane mirror. We went through part of the rules. And I'll just talk about the rules briefly. The first rule is that there's a plane mirror. And let's look at it for point objects. For point objects. So for point objects, the object looks like a point or dot. It has no head, no tail. So if I have this and I'm asked to draw a ray diagram, let me even clean the horizontal line for the meantime. So we have a point object. The rule is that if you have a plane mirror and ray of light incident on the mirror perpendicularly, so if the incident ray is such that it hits the mirror at 90, incident ray, the reflected ray is along the same path as the incident ray. So if rule one, if incident ray hits the mirror perpendicularly, or sometimes the word used can also be normally. Normally, the incident, the reflected ray takes the same path as the incident ray. So this arrow shows incident, the other arrow shows reflection, and they are all taking the same path. This is on condition that the ray hits the mirror at 90 perpendicularly. So I want to apply the first rule that a ray of light hitting this at 90 is reflected along the same path. Now, for an image to be formed, you need 2 or more reflected rays to meet or appear to meet. I take it again. For an image to be formed, you need 2 or more reflected rays to actually meet at a point or appear to meet. Please, did you get that? So,
Yes,
how many reflected rays do I have? I have only this one. I need at least another to meet or appear to meet at a point for an image to be formed. So, I draw another ray from the object. Incident ray, Now, to draw the reflected rays, one of the characteristics of images formed in a plane mirror is that object distance and image distance are the same, right? So the distance from the mirror to the object and then the distance from the mirror to the image must be the same. So what I'll do is that I have to measure this distance, because once there's the object, I have the object distance here. Let me assume this is X by my, okay. So I take the same distance, X at the other end. So it would, here, if you want to measure, if this is, when you measure, this is around 50. It's been cleared. I can't see properly. This is around, I think, 13. It's around 13.5 centimeters. I measure the same 13.5 centimeters at the other end. Okay, so this is ideally, this is where the image must be, because object distance is equal to image distance. So you must get that, so that this is the incident ray. The reflected ray can be traced to this, traced to that point, because for an image formed by a plane mirror, this must happen. So I must trace my reflected ray to this point, else I'll not get this rule that object distance is equal to image distance. So this is the reflected. I can draw another one, another incident ray from the same object. From the object, I need at least 2 though, but I can do it for 3. Then to draw the reflected, you must trace it to the same point. So I have my 3 reflected rays. 1, this is 1, 2, and 3. Where will be the image? I said for an image to be formed, 2 or more reflected rays must actually meet at a point or must appear to meet. When I look at what I've done, 1, 2, 3, the reflected rays, do they look like meeting one day? Do they look like ever meeting? No, they are getting diverged the more. I can extend the rays, but they still look like diverging. So there's no way they will meet in front of the mirror at all, at where the object is to form an image. So what I have to do is that, okay, I can extend the reflected rays backward, extrapolate the reflected rays backward. That is why you must trace it to this. So the rays appear to be meeting over here. And that is the point where the image is. the rays appear to be meeting over here. That is the point where now, because this image is formed as a result of the virtual or apparent intersection of the reflected rays, a virtual image is formed. This image will be virtual. Why? Because the ray formed is as a result of the apparent intersection of the reflected rays, image formed as virtual. So a virtual image is formed whenever two or more reflected rays appears to intersect at a point. If you have any question, ask me. If you have any question, ask me. So if the reflected rays actually meet in front of the mirror or at the side of the object, the image formed will be real. So if an image is virtual, the explanation is that one, it is not formed on a screen. Two, it is formed as a result of the apparent intersection of two or more reflected rays. Then image form is virtual. Okay, Abdullah, noted.
Thank you.
All right, then let's look at an extended object. The image formed if the object is extended. An extended object has a head and a tail. You see this one, the point object, there is no head, there is no tail. But this object, this object in consideration, which we are going to look at anyway, has a tail and a head, hence an extended object. Can I clean this? Can I clean the ray diagram?
Yes, please.
For plane mirror, a virtual image will always be formed, no matter where you place the objects. For plane mirror. So we have an extended object. The arrow represents the head. This is the foot. This is for extended objects. How do I use ray diagram? To show the nature of image formed. So object distance is always equal to image distance. So this distance very, very important. Or measure or use a straight edge to take your measurement. Around 14. So around 14, the same point. Because object distance is always equal to image distance. So a ray of light hitting the mirror at 90 goes undeviated. So incident incident as against reflection. This part is indicated as broken line because the image is virtual. The image isn't actually formed at that point. Okay, the reason for indicating that as a virtual. So straight away you have the position of the foot. We need the position of the head. Now, if this is the head, object height equals image height. It doesn't change. So if the object height is this, the image height will also be that. Or take a ray of light, but if you are going to use this, then you must get the object height. Okay, this is about 6. So I measure the same thing, 6 centimeter, I mean. Though I can join, but I want to also use a ray diagram that a ray of light hitting the mirror perpendicularly reflect along the same path to connect the head. I can just join to form it, but I want to use 2 or more rays to indicate the head. So a ray of light hitting the mirror at an angle must reflect, okay, to obey the law of reflection. But you must trace the reflected ray to where the image will be, the reason for measuring it. So this is the reflected ray, and this is the point where the 2 rays appear to meet. When you join it, you have the image. Okay, I did the foot using 1 ray. I can use another ray because the image must be formed by 2 or more reflected rays. So I can use another ray. Coming from it at an angle must reflect at the same angle. So I formed a foot using two reflected rays, and I formed the head using two. Okay, you don't use a lot of rays, maximum 2, 3. If you use a lot of rays, it's like you are littering around with rays. You are littering around with rays. This also, oh please, all rays must be indicated by arrows. So incident reflected, incident reflected. This part is broken because it's virtual. So this is the image of an extended object. Any question? Do we have any question? Amma, Lizzie,
Sir, please, so this one is still a virtual image.
pardon?
It's still a virtual image.
Yes,
Okay.
because it is still formed as a result of the apparent intersection of the reflected rays. Look at the reflected rays. 1, 2, 3, 4. It is getting more dispersed as the rays move. So there's no way they will meet in front here. If they could meet in front here, it will give you a real image. But because they can never meet in front, the reason for us extending the rays backward to form the image. Right.
Okay. So, sir, what you've done there, can it be a perfect example for a pinhole camera?
For a pinhole camera, the image is formed on the screen. Okay. This is a perfect example of the image formed by the plane mirror.
Okay.
All the images formed by a plane mirror is virtual.
Okay, sir.
All right. Then we are saying that images formed in a plane mirror are laterally inverted. Let's see if we can use a ray diagram to form an image in a plane mirror which is laterally inverted. So I'm using the letter P. Or let me even use the letter F. F can be drawn easily. As for P, the head will be some logology something. Oh, but anyway, we can still do it. But let's do it for F. How do I use a ray diagram to show lateral inversion of the letter F? So the distance of the object from this point to this point must be the same as the image. So I must take this measurement. Very, very important. So this is 17.5. And so I measure 17.5 from the other end. 17.5 is somewhere here. So, and I'm taking this measurement because object distance, image distance, always equal for plane mirrors. And the ray is hitting the mirror at 90. So the ray coming from that point is 90. So incident reflected. So this will be this point, the foot, the same rule is to be applied to this point as well. And the same rule here. Now, when I join the 3 points, I have this side. Okay. I have to measure from here to this point, from here to this point. So, and the same distance also there. So if I have the same distance, then I can just deepen this one so that it won't be different. I can even clear this so that it will show me the F laterally inverted properly. Is my F laterally inverted?
Yes, please.
Yeah, but is my F laterally inverted? Oh, yeah, but is going to sleep. So try it for P. Try it for P. You draw some isometric drawing P. Try it for P. Charlie. I pause the video. Can you hear me?
Yes, please.
Okay. So this is the mirror. Let's assume the phone is a mirror. Light is incidenting on the phone, on the mirror at an angle theta. And that's what I've drawn for you. Okay. When the mirror is purely horizontal like this. Okay. Now I decide to rotate the mirror through an angle. Okay. When it's like this, I turn the mirror at an angle, either clockwise or anti-clockwise. That's what I mean by rotation of the mirror. Class, are we okay? Class?
Yes.
Okay. Now, so I'm rotating the mirror through an angle theta. But when you do that, when you rotate the mirror, it doesn't change the position of the incident ray, the source of light. So I've rotated this mirror through an angle theta, alpha. It doesn't change the source of the incident light. The reason is that maybe you are directing the ray from the sun. You can rotate the mirror, but can you go and then change the position of the sun? Class, can you do that? No.
No, please.
Maybe you are taking the source of light from a bulb. You cannot change the source. So under this rotation, we are always maintaining the source of light. But what will happen is that, let's assume this is, the marker is the original mirror position M1. Crystal, are you there? Inshira, all the insurers, are you there?
One is here.
Yes, please.
So
The other one.
let's assume M1 is the original position of the mirror. This is the first normal when I haven't rotated it. Please look at what I'm demonstrating.
Sorry.
So this arrangement is the mirror. This is the normal N1 when I haven't rotated the mirror. When I rotate the mirror through an angle alpha, see what will happen to N1. I'm rotating it clockwise. What is happening to the new normal? You are not observing.
It's becoming the reflected ray.
Hold on. There's the normal. There's the mirror M1. There's the normal N1. When the mirror is not rotated. When you rotate the mirror through an angle alpha, what happens to the normal? The normal position also changes by the same amount of rotation. So if you rotate the mirror through an angle 30, the new normal would also rotate by the same margin. So the moment you rotate the mirror, there will be, the normal is always a perpendicular line to the mirror. When the mirror is not rotated, that's the first normal, N1. The moment you rotate it, we will certainly have another normal. Okay, but the position of the new normal, which must also be still perpendicular to M2, will be this. This is N2. Now you realize that the angle between N1 and N2 is equal to the angle of rotation, alpha. The mirror is rotated through an angle alpha, and the change in the old normal and the new normal would be equal to the angle through which you have rotated. Let me take that again for you to see. N1, when the mirror is not rotated, this is its normal. This is its normal. When you rotate the mirror through an angle alpha, this is how the new normal would also change. So if you rotate the mirror by an angle of 30 degrees, the angle between the old normal and then the new normal will also be 30. Please, are we okay?
Yes, please.
Yes, please.
Okay. Now, once this is the new normal, it means that the new incident ray, angle of incidence, will be between N2 and the source. This will be the new angle of incidence. This is the first angle of incidence, I1. This is I2 with respect to the rotation of the mirror. Then we must have for the second, the first situation, This is also the angle of reflection, which is also equal to I1, because angle of incidence equals angle of reflection. So from here to here will be the same as from here to here, but we are bringing it upward here. So if there's I1, this will also be I1. Please, are you seeing the picture? Then, if this is the new angle of incidence, there must be a new angle of reflection. This distance, our angle must be the same as this. So, we must have this as the new reflected ray R2. And the magnitude is from N2 to R2. Are we there? Are we seeing it?
Yes, please.
All right. Now, we are going to analyze this to come up with something. The purpose of this whole rotation is that when you rotate a mirror through an angle theta, what happens to the two reflected rays? This is the old reflection is R1 and the new reflection is R2. What happens to the angle between the old reflection and then the new reflection? That is what we are looking at. Okay, now let's find, assuming this is A point O, N1, N2, R1, and then R2. I want us to look at angle A, O, N2. I mean this angle. What is angle AON2? This is equal to this angle I plus this angle alpha. So this is equal to I1, the old angle of incidence I1 plus the angle of rotation is N2. Are we okay? Now, I'm talking about angle AON2. Okay? AON2. It is this whole angle. Now, this angle AON1 is I1. Let me even call it I, or let me call it I. AON1 is the first angle of incidence I. And then this angle is alpha. Okay, the angle between the two, okay, normals, N1 and N2 is alpha. So this whole angle here is equal to this angle plus this angle. So angle AON2 is equal to I plus alpha. Okay, which must also be equal to the angle N2OR2. I mean, this whole angle, because this is angle of incidence and this is the angle of reflection, and they are all equal. So this must also be equal to I plus alpha, because angle of incidence is equal to angle of reflection. So angle N2OR2, which is this whole angle, must also be equal to this. But what we are interested in is that we want to determine this angle. Angle R1OR2. We want to determine this angle. Now we know this whole angle, which is this. But if we could determine the small angle, we could easily subtract, and we have this angle. Please, are you seeing the analysis? I hope you are following it. We are interested in this angle. This angle is part of this bigger angle, N2OR2. So if we could find this bigger angle, then we'll subtract this small one from it to get this, where the question mark is what you are looking for. So if we know this whole angle, which is this, but if we could determine this small, we could just subtract it from it to determine where the question mark is, which is angle R1OR2. That's what we are looking for. So angle R1OR2 is equal to angle N2OR2 minus this small angle N2OR1. N2OR1 is the small angle we are looking for. If we could get it and subtract it from the bigger angle, we will get N2OR2. Please, are you following it? Are you following it?
Yes, please.
So the question is that, how do we determine the small angle, N2, angle N2OR1? Open your eyes and watch. We know this angle. We know this angle to be this whole angle, N1OR1. Angle N1OR1. This angle is equal to I. This angle is equal to I. Angle of incidence, angle of reflection, they are all equal. So N1OR1 is also equal to I. Then we have this angle, which is part of N1OR1. Okay, we have this angle, which is the angle between the new and the old number, N2 and N1 alpha. So it means that this small angle N2OR1 is equal to N1OR1 minus N1ON2. N1OR1 is I minus N1ON2. N1ON2 is alpha. And so we found the angle N2OR1, which we are looking for. Okay, so when we substitute this here, angle N2OR2, which is this, I plus alpha minus angle N2OR1, which is also this, I minus alpha. This, let's expand, minus I plus alpha, minus I, then this time this plus alpha. I will cancel, which is equal to 2 alpha. And this is the angle between the old reflected ray. This is the angle between the old reflected ray, R1, and the new reflected ray, R2. It is always equal to 2 times alpha. Now, what does it mean? Alpha is the angle of rotation of the mirror. So we initially rotated the mirror through an angle alpha. We've managed to prove that whenever you rotate a plane mirror, okay, its effect on the reflected ray is equal to 2 times the angle of rotation. So when you rotate a mirror by 15 degrees, when you rotate a mirror by 15 degrees, the angle of reflection between, or the angle between the two reflected rays is twice the angle of rotation. So rotated by 15 degrees, the angle between the reflected rays will be 2 times 15, which is 30. Rotated by 10, the angle between the reflected rays would also be 2 times 10, 20. This is the concept we are proving. Please, if you have any question, quickly ask, because we have 8 minutes to end. If you have any question. Okay, but that is the concept. The concept is that maybe in our next meeting, I'll go through this once more with you about how to come up with the fact that the angle between the reflected rays is always twice the angle of rotation. But the concept is that whenever you rotate a mirror by an angle, whenever a mirror is rotated, through an angle theta, the reflected rays also rotates by an angle equal to 2 times the angle of rotation. So if the angle of rotation is alpha, therefore, if angle of rotation is alpha, the reflected rays also rotates by 2 times alpha. That's the concept I'm developing. Class, are we okay? Class,
Yes,
Miss Stadia,
hello.
please, when you're cleaning the downside, you cleaned after the end too.
I clean after the,
The minus N2.
this is N2OR1.
Okay.
So you rotate it by 10, the angle between the old reflected ray and the new reflected ray will be 2 times the angle of rotation. So 2 times 10, which is 20. That's the whole concept. And over here, it's on condition that we are always maintaining the source of the light. It is at that same point. We are not changing it. So this is the nitty-gritties of the concept of rotation of the mirror. If you have any question, ask. If you don't have any question, then Ekwe Adoma, Charlotte Adoma, Priscilla,
Yes,
Lynn,
yes,
Amma,
please.
Euresi. This is where I draw the curtains on today's meeting. Okay, until we meet again, probably the same time Monday. In fact, may God be with you and bye-bye.
Bye.
Bye.
Can I off it? Or some of
No,
you are
I'm still copying.
okay. So if you rotate the mirror by X, if you rotate the mirror by X, the angle between the reflected rays would also be what?